that would be a crowd pleaser if they had something like that worked.
Yeah. Our atmosphere is 100 times denser, so it's a little easier to make it fly. Okay, David Levy, do you have something for us tonight, and would you like to read it now?
Yes, I would. Thank you.
Sure.
Thank you very much. Wendy and I are giving you a sunny and cool welcome from Vail, Arizona right now. We wish you all good health. We hope everything's going well. Today is the 18th of February, and most of you young'uns think that this is the day that Perseverance landed successfully on Mars. But for older people, like most of us, February the 18th, 1930 was the day that Clyde Tombaugh discovered Pluto. And it's something that we are definitely remembering, whether or not we still consider Pluto a planet or not. I have here a quote that I'd like to read, and it's directly from Clyde Tombaugh himself. He said it while I was interviewing him for Chapter 4 of my biography. Chapter 4 was called Discovery's Wake. And Clyde had a few things to say about discovery that I'd like to quote to you here. He said, "You have to have the imagination to recognize a discovery when you make one." When they examined the Voyager images and saw for the first time the volcanic eruptions on Io, that called for some intuitive imagination. I would suggest that above everything else, in observing, you have to be very alert to everything. You have to be able to recognize a discovery as such. There are so many people, both professional and amateur astronomers, who do not seem to have that talent. An astronomer, whether professional or amateur, cannot afford to be in such a rut. I might say that different types of personalities in astronomy make certain types of discoveries that are in line with their personalities. That quote is directly from Clyde Tombaugh, and I wish you the best of luck, and let's enjoy our meeting tonight. And now back to you. Thank you.
Okay, thank you, David. Next, I'd like to call on Dale Teamy, who has our In the News and In the Sky reports for tonight. Dale?
Okay, thank you, Dale. So tonight for In the News for February 18th, we have nothing. Here we go. Well, we had our 7 minutes of terror this afternoon. I imagine a lot of us tuned in while we were watching the Perseverance landing. So the Mars 2020 mission, including the Perseverance lander and Ingenuity Mars copter, successfully landed on the red planet just before. Hello?
Hello? You're there.
Okay, yeah. Before 4 p.m. Eastern Standard Time today. The final moments of the journey to Mars, including the infamous 7 minutes of terror, radio blackout of re-entry, were carried on NASA TV for our participation and enjoyment. So enjoy this historic snapshot of the mission's first moments on Mars. Perseverance will settle in for a few days before getting down to science at Jezero Crater, including the search for past evidence of life. As of right now, Mars is hopping. The Martian New Year just began on February 7th, and 3 spacecraft showed up for the party. The Hope Orbiter, a United Arab Emirates mission launched on a JAXA rocket, the Chinese spacecraft Yuan-1, and now Perseverance and Ingenuity. Now on February 10th, just 1 day after arriving in orbit around Mars, Hope captured a stunning photograph of the red planet. The new photo shows a smattering of clouds, 4 massive Martian mountains, and the vast Valles Marineris, the largest canyon in the solar system, on the right side of the image. We couldn't have asked for a better day on Mars, UAE Space Agency Chairperson Sarah Al Amiri wrote in a tweet Sunday. Can't wait to see the science data come in so we can comprehensively characterize the lower atmosphere. Now, if some of you are skeptical NASA will indeed be sending humans back to the moon in 2024, well, NASA is starting to fess up to the you might be right. The previous president set an ambitious timeline for the Artemis program, but given that a new rocket, capsule, lunar lander, and other components still need to be developed and fully tested, acting NASA admin Steve Jurczyk admits that over the next 2 to 3 months, NASA must decide if the program needs a different schedule. Outgoing NASA admin Jim Brizendine was unwilling to back down from the 2024 deadline in public. The Federal Aviation Administration said it will oversee an investigation into a crash landing of a SpaceX prototype rocket, Starship SN9, on Tuesday. The announcement comes after the FAA forced SpaceX to delay the launch as it investigated a previous explosion of a similar rocket prototype. The destroyed SN9 was an early prototype for a rocket the company hopes will carry the first humans to Mars. Launched in a high-altitude test flight on 2-2, the vehicle carried a few miles up into the air, hovered for a moment, and then conducted a belly flop-like maneuver on descent before making an explosive landing back on the launch pad. SpaceX CEO Elon Musk, who used Twitter to publicly bash the FAA last week, wrote Tuesday morning that he would be off Twitter for a while. Now, the European Space Agency announced February 16th that its first call for new astronauts in more than a decade will be open to candidates with physical disabilities. During a briefing with reporters, ESA officials said the agency plans to recruit 4 to 6 career astronauts and a pool of approximately 20 reserve astronauts, a first for ESA. Additionally, in another first for the agency, outgoing ESA Director General John Warner announced that it is looking to recruit its first pair astronaut, someone deemed psychologically, cognitively, technically, and professionally qualified, but who would have a physical disability that would normally prevent them from being selected due to requirements imposed by current space hardware. There are many unknowns ahead of us. The only promise we can make today is one of a serious, dedicated, and honest attempt to clear the path to space for an astronaut with disability, ESA said in a statement. And now to In the Sky for February 18th. Yay, moon. On Saturday evening, February 20th, the pole-to-pole terminator boundary that divides the lit and dark hemispheres of the waxing gibbous moon will fall just to the left or lunar west of Rupes Recta, also known as the lunar straight wall. This feature is very obvious in good binoculars and backyard telescopes. The Rupes, Latin for cliff, is a north-south aligned fault scarp that extends for 65 miles or 110 kilometers across the southeastern part of Mare Nubium. That is a large dark region in the lower third of the moon's Earth-facing hemisphere. The straight wall is always prominent a day or two after first quarter and then again just before the third quarter. For reference, the straight wall is located due north of prominent crater Tycho. On Sunday night, February 21, the moon will cross a large open star cluster known as Messier 35, or the Shoe Buckle Cluster. After dusk on Sunday, the waxing gibbous moon will be positioned several finger widths to the lower right of the cluster. Hour by hour, the moon will approach the cluster. By the time the moon sets after 3 a.m. local time, observers in the Eastern Time Zone will see the moon only a finger's width below the cluster. Observers farther west will see the moon pass across the cluster and leave it behind before moonset. To best see the Messier 35 stars, hide the bright moon behind the upper edge of your binocular's field of view. Then, after dusk on Wednesday, February 24th, the nearly full moon would position just 2 finger widths to the upper left or 2 degrees to the celestial north of the large open star cluster known as the Beehive, or Messier 44, in the constellation of Cancer. The moon and the cluster will both fit within the field of view of binoculars, the red circle, but the moon's brilliance will mostly overwhelm the cluster's stars. To see more stars, try placing the moon just outside your optics field of view. On Tuesday evening, February 23rd, observers in eastern continental USA and Central America can watch the waxing gibbous moon occult the medium bright star Kappa Geminorum. Observers in Canada and South America will see the moon graze or slowly miss the star. The dark leading edge of the moon will cover the star first, causing its point of light to wink out. The star will reappear from behind the bright eastern limb of the moon sometime later. Ingress and egress times vary by latitude. Use Starry Night or another astronomy app to look up the times where you live. You can report your data to IOTA. And that finishes in the news and in the sky for February 18th, 2021. Thank you, Dale.
Okay, thank you, Dale. Okay, so at this point, we open it up for observer reports, but before we do that, I'd like to say that depending on how much discussion we have during observer reports, if there's a little time at the end, I will open it up for something we haven't done for a while, and that's ask a dumb question. Okay, so I want you to tell you that so you can be thinking about it. If there's a question about astronomy that you've had for some time and you felt a little awkward about asking or didn't know who to ask, I hope to give you a chance tonight. So who has an observer's report?
I think we should start with David Levy before I go into my treks in the north.
Well, thank you. My observer's report comes from just a couple of hours ago. There are no new sunspots on the sun that I saw today. However, there were 7 prominences, which is about normal for this time. But what was unusual was a very long filament, a dark filament on the surface of the sun, on the photosphere, seen through my hydrogen alpha telescope. Didn't take a picture of it, but I could describe it as being probably about 3 or 4 times the diameter of the Earth. And it's just a very long, beautiful filamentary structure on the photosphere. I just wanted to point that out to you. Thank you.
I got some astro photos that I'd like to share at the break, but Adrian, why don't you go ahead?
Okay, I will just share one photo. I got my chance to see light pillars in action, which is something I had heard of. I had heard other people see. The light pillar picture that I'm showing actually did end up on the front of spaceweather.com for February 14th. So I thought that was really cool when that happened. So let me pick it out here. I'll share that photo and let's see if this works. At least I thought I picked the photo. Okay, here we go. We're preparing to share the photo. And okay. Everyone see that one? This is up at Alcona. That's Alcona Dam Pond out at the Alcona campground. And
That's beautiful.
that is facing Curtisville, if I'm not mistaken. And all of those light pillars came into view. We had it, there was a haze. And whenever there's a haze, that means when I image the night sky, I'll get the larger stars and the constellations to show up a little bit larger. So it makes for a really beautiful sky shot. So there's a little something of everything in that photo. And those are light pillars. Those who don't know what light pillars are, it's not the aurora. I'm actually facing southwest, or well, no, I'd say northwest. It's west, and they are light coming from mostly man-made light with flat ice crystals that are floating in the air. Sometimes you can feel the ice crystals. It feels like it's snowing a little bit. those flat ice crystals refract the light and basically shapes it into a column. So all of those lights that are in that distant town are being refracted into pillars. If I'm lucky, okay, no, it's only gonna. There are a couple pictures that I took, but that's the one that ended up in spaceweather.com. If you go to spaceweather.com, you'll see it written up, February 14th edition. I'm underneath a beautiful aurora that was taken in Norway, so it's a bit of an honor to have an image of mine next to such a beautiful image from northern part of Norway. So Norway is north. So that is my observation report. I've got other photos, but I am going to stop sharing so that others can share their fun out into the cold.
Congratulations on getting into spaceweather.com.
Thank you.
And a beautiful photo.
Yeah. Who else?
Well, I have one photo to share. I went out on Tuesday, and I think it was Tuesday. Was it Monday night? Tuesday night? Tuesday night. And I have my small wide field set up. I got a new filter. It's an IDAS NBZ filter. Supposed to be good for fast focal ratios. It's a dual band filter. And I captured the Spaghetti Nebula. So it's a very, very faint nebula. Can everybody see that?
See it? It's
Yeah, we see it. Looks really nice.
It's a bit noisy. This is 4 hours of integration, but it's so faint I really had to jack it up. These are 5-minute images with that filter. It's a dual band H alpha and oxygen 3. So I'd never seen it before. It's quite large, 7 full moons. So that was my image for the night. I processed that
How
today.
dark was your observing place?
I was in the backyard. There's snow everywhere, so I mean, 20 yards away is an overhead light that I can't turn off. It's a power grid light. But I'm in Bortle 5, suburban.
Okay.
But with that duo band, I mean, that filters out a lot. Oxygen 3 has a little bit more light coming in than H alpha for pollution wise, like moon glow and so forth. But I'm not sure how much the snow reflects back up or not. But in a full moon when you're out in the snow, it seems pretty bright.
Yeah.
So I think with more integration time, I can bring out some of this. And in fact, I think a lot of this might be my processing skills as well. But anyway, I'm learning. But it is a very faint target that's not easy to get. So fast optics and a wide field of view. It's 135 millimeter focal length. So
Okay.
Yeah.
Very nice.
yeah.
Oh, well done.
Who else? Anyone else before we ask for a dumb question?
I got
Dumb question. How do I turn that off? Stop sharing. There we go.
Any other observing reports? It's been almost too cold to go out and do observing.
I was asking Doug earlier about that. If break a cable, I was concerned.
Yeah.
Yeah, see, I was gonna go out and I braved the cold that night, but 2 nights later it would get down to like sub-zero temperatures, and I disappointed everybody by not going out there with my camera to brave the cold. I decided sleep was probably more important. That's my excuse, and I'll stick with it.
The only thing I have is from 2 weeks ago. Just a quick fun thing. Let me see if I can find it here. Where did I put it? It's my ISS pass. Oh boy, why can't I find that? Well, somebody else go on. Somebody else go ahead.
Okay, anyone else? Do we have a dumb question?
I do. Kind of a holdover from the previous meeting. What's harder to define, a planet or a lenticular galaxy?
I would vote planet. And I think the only reason I'm voting planet is because along with the definition comes emotional attachment to the discoveries from the past and even the naming of the planets and the fact that all of these worlds are active and as far as the lenticular galaxies go, and I'm kind of going out on a stretch, there's a little less emotion about deciding whether a galaxy is lenticular or not. It can be debated, but not as fiercely. So kind of an out of the box answer is the politics of debates over planets versus galaxies is a lot different. So there you go.
Good point. Is that a good answer, Jeff?
Yeah, I mean, I'm sure the galaxy community fiercely debates it, but yeah, I would agree that for the general public, planets are, I mean, most people never even heard of a lenticular galaxy.
Well, I don't know. Does the galaxy community redefine the definition of a lenticular galaxy when debating it? Because the planet people do.
As far as I know, the definitions for lenticular are pretty vague, and there's quite a bit of crossover where certain people would call it one thing and other people call it something else.
What does lenticular mean?
Good question.
So Wikipedia says a lenticular galaxy, denoted S0, is a type of galaxy intermediate between an elliptical, denoted E, and a spiral galaxy in galaxy morphological classification schemes. It contains a large-scale disk, but does not have large-scale spiral arms. Lenticular galaxies are disk galaxies that have used up or lost most of their interstellar matter and therefore have very little ongoing star formation. There's some further definition, but I instantly thought of the of M104 as a good example of a lenticular galaxy.
Yeah, I mean, from what I've seen, a lot of times if a spiral's just edge on, if it doesn't have star forming regions that are obvious, but sometimes it's hard to tell whether they're being blocked by dust, they can get classified as lenticulars.
Yep. If I'm not mistaken, the sombrero is basically your poster child for a lenticular galaxy, but I'm not seeing it listed here. I'm seeing a couple of others that are listed that are shown as the lenticular galaxy. So
Okay. As dumb questions go, I would say that was on the smart end of the dumb scale. Anyone else? Before we give it back to Doug for his images. Okay, Doug, what do you have for us?
Okay. Okay, so the first one here is back on February 3rd. Yep. There was going to be a ISS pass directly overhead at my location, so I decided to put my 10 millimeter lens on my Canon T3i, which is piggybacked on my 10-inch, and opened it up for 10-minute exposure at a ISO 100 and f8, so that I could take one single image while it was traversing across the sky. And so you can see I've got, let's see here. I've got the Orion on its side right here. I've got the Hyades, the Pleiades, and then Cassiopeia up here. And it traversed from the northwest to the southeast. So it kind of sliced right through Cassiopeia, down through here, and out again. So I got the entire path that lens could cover. It actually was outside the field of view for a little bit until it got hit Cassiopeia. But that's the ISS pass that happened on the 3rd.
You know, if you could have imaged the Milky Way, you would have had an ISS splitting the winter Milky Way with that shot.
Yeah, and I think if I were to do this again, I'd go at ISO 200 or maybe even 400 to get a little more depth. But I didn't. This was kind of an experiment with this lens at that exposure time. I didn't want to overexpose it by, my usual ISO is 1600 or 3200 when I'm taking my 30-second shots. But this was a 10 minutes, a single shot. Any comments on that? Okay. Also, on that night, I went after Thor's helmet. And this is 156 times 2 minutes each. So about 300 and some minutes of data. Thor's helmet is out in the southeast to south for me when I'm taking it, and it's in the Detroit metropolitan sky glow that I have, which is 50 miles away. But it's the first time I've tried this one, so that was kind of fun. And then in the morning hours in the morning hours, I decided to go after this group, NGC 2336, which has got this couple of spiral galaxies here. So that's what I went after on the 3rd. And I think that's the last time I had my system up and running. So it's been over 2 weeks now.
Doug, what kind of filters are you using? Narrowband filters?
No, I'm using no filters at all. I'm just running one-shot color cameras.
Even the previous shot when you had some Detroit sky glow?
Yeah. A lot of the light pollution can be taken out in processing, but in that previous shot, the details of the filaments out there weren't going to show up because of the sky glow is actually brighter than the dimmer parts of that nebula. That's the downside.
Yeah, Dale, these new Apple and Android phones are just amazing. You just point them at the sky and that just comes out.
Very nice.
So, yeah, there was a question on YouTube about, I'm going to go back on video. There was a question on YouTube about astrophotography and the cameras that are used. I'll see if I can find it again.
I'm reading it right now.
It's in the chat.
Yeah, it says.
Yep.
Yeah. My answer to that is depends on what the astrophotographer wants to accomplish.
Doug, could you repeat the question, please?
Yeah, the question is, do most of the astrophotographers in the club use a mono camera or color camera? Dedicated astrophotography camera, not referring to a DSLR. Again, what I would say is that it depends on what the astrophotographer chooses as their targets and their desires of what they want to accomplish. I, for one, use a single shot color camera because I'm not willing to take 30 or 40 hours worth of data because I don't think I'm going to have that many clear nights in a row to accomplish something like that here in Michigan, especially during the winter. I mean, I've only had 2 clear nights in the last 18 days that I would have been able to shoot. So one night in winter, I might be able to get 11 hours in on one night on one object. If it's up for that length of time, it has to actually be up that length of time. In the case of Thor's helmet, it's only, it's up most of the night right now, but very low in the south. So you got to pick it off at around 18 degrees. It gets up to, I think, about 30 and then back down to 18 and in the trees for me. So I may only get about 3 or 4 hours on that object on any given night. So I'd have to wait until the next clear night, which might be the next full moon. I don't know. So when you're using narrowband, you usually are doing that with monochrome, and you have to, for every 1 hour of one filter, you're going to do an hour of all the other filters and then combine them all. So it really depends on what that astrophotographer wants to accomplish.
Hey, Dale, can you hear me?
Yeah.
Yes.
Yeah, to answer that question also, personally, I'm of the same opinion as Doug. I use a one-shot color camera also, simply because of just what Doug says. We don't have enough hours in this state to do RGB, red, green, and blue. But to really answer the question, I would think most of the astrophotographers I know, not just in this club, but throughout the Michigan community, do use mono cameras with RGB or narrowband. So they spend hours and hours, doing the different filters, and that produces a much better photograph. But like Doug says, I don't have the patience, to process all 3 filters at one time. So I like doing a lot of different images, per night or per week. But you do definitely get better photos from a mono camera with the different filters.
And I'd like to add to that another thought about that. Bill is correct that you can get outstanding results with monochrome cameras and using multiple filters across your data acquisition. But the other thing I like to do is, for example, I'll do the open houses for the club, right? Well, I'm going to use a one-shot color for that, no brainer. And I'm only going to take 30 minutes of images and stack them live for people to see, and then move on to the next object. So there's an example where a one-shot color is really kind of ideal. You're just going to take some quick stuff.
And if you can use a one-shot color camera and take, 5 to 10 hours worth of data, and you're going to have a darn good photograph. I mean, even, like the guys are using these new narrowband filters with their one-shot cameras, with the moon and the light pollution, they're getting some darn good pictures with their one-shot color cameras.
I might read between the lines and say if the person asking that question is asking because they're interested in perhaps choosing a camera and they've never done astrophotography before, it is more complicated to do monochrome workflow. And there's enough complications in starting it that you might want to start easier and do one-shot color for that reason.
Yeah, one shot is a lot easier to do. You're right.
Yep, absolutely. And you can start with your DSLR.
Yeah, you could take this picture I'm showing here is my DSLR on a tripod, and that's a 16-second exposure with an 18-millimeter lens. And I started with my Canon doing time-lapse photography. I would take 1,000 images through the night, and I can do a time-lapse of, the rotation of the stars, etc. And the one thing you do is you're learning how to acquire data, and you're learning how to process that data, independent of whether you have an expensive system or not. That's a very simple system to do that. So you can start with astrophotography with just wide field DSLRs if you wanted.
Yep. And to answer the second question we have there, have you astrophoto guys encountered problems with the Elon Musk satellite swarms? Yes and no. When he first started coming out or launching those, he didn't have any reflective coatings on them. So, they would definitely interfere with our photographs, but it's gotten to the point where he's putting some reflective coatings and some light shields on them And once they start orbiting, they start out like a couple hundred miles up. They go high enough where they really have not interfered with my photographs. And the ones that do make severe satellite trails through our photographs, we can edit those out in post-processing. So to answer that question, I don't know about the rest of you guys, but they have not interfered with my photographs at all.
Listen, you guys, I don't want to stop this really interesting stuff, but I would say, for the record, let's take a 15-minute break from now until 8:30, and when we come back, we'll have our main speaker presentation, but go ahead and discuss.
Yeah, Bill? And,
Yes, Jimmy.
and anybody else that's into that thing, you realize that there's like 12, I think 1,200 of them now, but there's going to be 42,000 of them.
Yeah.
And even with the coatings they're putting on there, they're still visible, just barely visible. They're at 6 or 7 magnitude.
As long as they're in sunlight.
Right.
Exactly, for a couple hours. The new Vera Rubin telescope, the LSST, we talked about a couple of years ago, has made an estimate it's going to take 30% of their time for viewing off.
Jeff, I think are you about to show us an example of an image you took with some satellites going through it?
No, I'm not. I'm just making an observation that we really missed the boat. The astronomy community really missed the boat by not challenging what's going on.
Well, you know what, Jim? That's still under debate. Like I say, I can take a 20-minute exposure over the whole course of the night and not have hardly any satellite trails. So what you may be reading and what's actually happening out there may be two different things. But Musk is launching these satellites. There's he's going to have a ton of them up in orbit.
42,000.
Interfere with our professional observatories and stuff like that, but we'll see.
I've
you
got
would think by now, with all of the ones he's got up there, plus what's up there now, that we would have an issue in our photographs, but I don't. I can tell you I don't.
Yeah, what I've got an image that kind of shows that and using a DSLR and lens image of the Orion Nebula, and you can see streaks above, below, to the right and to the left. Some are geosynchronous satellites, and others appear to be streaks that there are clusters of streaks going through it. So there's you per frame you may get something going through your images, and if you're like me and you're taking even wider field images, you've also got planes to deal with. So and meteors. So there's a number of things that can that you have to sort of filter out taking multiple frames.
I think in the middle of the go ahead, Doug.
I think the pros have more of a problem than we do because we're amateurs, okay? And
I understand, Doug, but the problem is just starting.
Oh, I know. There's going to be 100,000 of them. Yeah,
there are going to be 100,000 of them, and they are magnitude 6 to 7, and they're going to be essentially just floating off the sky.
They are in fairly low orbit,
That's right.
lower than most satellites would be, and that means that they're only, as Doug said, only visible in sunlight, and so only near post sunset or pre-sunrise. Now, Gordon Hansen and I did a discussion on this, and due to the tilt of the Earth, in the summertime, we figured out that there is a point in the very center of the summer by the summer solstice where if you are, I would say, north of the north shore of Lake Superior, there is no time of the night that you would not be able to see some of those Starlink satellites in some portion of the sky. The farther south you get, the safer you are. But in wintertime, you'll almost never see one of those Starlink satellites.
So that's a good thing, Jim. Like Tim and Doug say, it depends, you know, what time of night you're looking, because
Right.
you know, they're fairly low altitude.
Well, that's true. But all I'm suggesting is that you might want to pay attention, because the astronomy community, both amateurs and professionals, essentially just let this happen without being getting any input to it. And I just saw a presentation. If I could find the link, I'll send it to you.
No,
I'll
I get
send
it.
To
Yeah.
the groups just a couple of days ago from Quebec, of a lady who's doing research on looking for near-Earth objects and everything. And the last 10 minutes of it discussed this whole subject, and it's really a disaster waiting to happen. And I think you guys will be affected at some point.
Yeah.
That's all. Just look it up.
Oh, no, and
we've been talking about, in the astrophotography community around here, we've been talking about this for a long time. So, you know, we're concerned. Yes, we are concerned.
But have you written your congressman?
No, I have not. No.
I know, Bill. I'm just suggesting that's what should have happened, and maybe still should happen. There ought to be some controls on it, because there are none now from our perspective, and there's lots of people interested in doing what Musk is doing.
Well, it's probably a little late, Jim, only because it's not just Musk, it's several organizations doing the same thing, including other countries where we would have no say.
So,
if I'm not mistaken, the whole idea is behind it is supposedly to spread internet to places that typically don't.
Sure it is.
So think about it. Who's going to have the bigger hammer?
That's right.
The rest of the world that wants internet, or us measly little amateur astronomers? It's going to happen whether we do anything about it or not.
All I'm saying is we didn't have a hammer at all, and nobody considered what they're doing from the shielding the whole Earth for maybe the next century for serious observations.
Yeah, what's probably going to happen is our children grow up and get into astrophotography. The skyscape is going to change to the point where especially in the darker skies, it's much more apparent that these satellites are out there. And it's the one thing that I noticed. I took a 90-second and a 120-second exposure, got plenty of satellites above and below the target that I was shooting at. So it is out there. I don't know I know I've seen some things online where astronomers were trying to mount some kind of, I don't want to say offensive, but they were trying to do something to appeal to Elon Musk and to all these other companies to do something about all of these satellites that they're launching. I don't know if one of the things that they're doing is giving an alternative solution for the internet problem that they're supposedly out there to solve. Is it just about the internet? I don't know. I would guess that there's something else that those satellites are out there to do.
It was motivated primarily by stock market trading. His mechanism for communication is faster than ground-based, but the markets are only open for so many hours, and so he had all this excess bandwidth, and that was like, hey, we could use that for internet for underserved areas, which is a great idea. But again, I keep going back to the close to sunrise and sunset, except in summertime. So it's kind of where you are on the planet and what season of the year it is and what time of the day you're shooting, whether it would even impact you at all.
Yeah, and again, I'm up in bortle-free skies up there west of Cadillac, and in those dark skies, you can visually see satellites all night long. But again, I have not experienced Musk's Starlinks. Hardly at all. And I can tell you another thing. I don't have internet up there, and I welcome Musk's internet service up in my area. So it's a double-edged sword, like Doug Bach said.
Yeah.
You know, who wants more? Who wants internet, or who wants astrophotography?
Hey, Bill, just
Yeah.
for your information, I'm out here in Arizona now. One of the astronomy clubs I belong to has got a guy in it who is signed up for that internet service. He's up in northern Arizona, up around Heber, Overgard area.
Agus?
No, not Agus. This is another guy, but he has has no high-speed internet coverage, but he's signed up for this service. So
Yeah, I agree. I'm going to be like one of the first ones to sign up also. Because he doesn't fly his satellites over my observatory.
Do you need to have thousands of satellites to get internet? Can't you have 50 or 100 well-placed satellites that would be larger, maybe more powerful, and they could cover the whole planet?
Here's
nice, but then again, they're larger, so larger streaks.
Here's how they're doing this to keep the latency down, is to put them up only 100, 150 miles up, so there isn't a lot of latency. Because yeah, you can go with geosynchronous satellites, but they're 25,000 miles out, and your latency is huge then. So what he's after is low latency down in the 50 millisecond range, and what'll happen is your signal will be passed along as the satellites go over you. That's what they're working on, is trying to keep the latency down to something around 50 milliseconds as opposed to 3 seconds.
I was just going to tell you, I talked to my brother in New York, and he says it's $90 a month. He was going to sign up.
Yeah, something like that.
Yeah.
Pretty cheap.
I don't know if anybody else heard.
I had not heard a price, but
It seems pretty reasonable considering it works anywhere on Earth. So
I agree. Yep.
We've come up with all of the practical uses, and when it's cloudy, there isn't much we're able to do, and that's when we wouldn't care if the satellites are up at that point. But still, Jim, to the point that you're making, that looking for faint objects and looking for, doing science is hampered. Now, I've heard that it doesn't hamper looking for doing things like parallax and getting distances of stars. Having a satellite actually crosses, eclipse a star when you're trying to study it. I guess the probabilities right now of that are slim, but there is a trade-off, and right now the astrophotographers are stacking enough images to get rid of those strays as they show up, and we end up with just the data. So right now it's working. I don't know in the future if it gets to a point where there's so many of them that we don't have good data. I imagine the outcry it's just gonna naturally grow as that happens. So yeah, we're kind of at a point where we're dealing with it right now for the greater good of internet. But unless a better solution comes along, it's going to be a fight for how we're already fighting light pollution.
Sure.
Now we're fighting satellites. That preserving the night sky for future generations is a huge battle.
Yeah, it is. It is. I just brought it up because it seems to me like this is one of those things that happen without us getting our licks in, without getting our message in it, our input into it, and not just us amateurs, but the astronomy community in general.
Yeah.
Listen, you guys, I hate to interrupt, but it's 8:30, and we need to move on. I would just add my own comment that I'm glad that SpaceX, once the problem was called to their attention, at least took some action to reduce the problem.
Yes.
I don't know by what factor they reduced the problem, probably
Not
at least
much,
a factor
not
of 10.
No, not nearly as bad. Just
Yeah. So let's be happy about that. And that sort of sets a precedent that if somebody else launches a constellation of satellites to compete with him, it informally puts expectations on them to not have them be super reflective. But anyhow, I think this was a great discussion. I enjoyed listening to it. I learned some things. We're about to learn some more things that are pretty esoteric, I think. Tonight, our speaker is Dr. Ilias Cholis. I apologize if I'm not pronouncing it correctly. Dr. Cholis is an assistant professor of physics at Oakland University. He's a theoretical astrophysicist. His work focuses on searches for evidence of dark matter annihilation and on the study of high-energy astrophysical phenomena occurring near very compact objects like black holes. His work also includes gravitational wave astrophysics, and in particular, the investigation of black holes as a dark matter candidate. His topic tonight is antimatter, cosmic rays, and dark matter. Dr. Cholis, thank you for coming.
Thank you for inviting me. I really enjoyed all the earlier discussions, and I actually realized that you probably know a lot of the things that I thought I would have to explain, but I will explain anyway. And of course, please ask me as many questions as I go along. So I'm going. First of all, everyone can hear me, right?
Yeah.
Yes.
Okay. So I am going to talk about how we use observation of antimatter cosmic rays to learn about dark matter.
Excuse me, Dr. Cholis. Could everyone mute your microphone during the presentation unless you want to ask a question? Thank you. Sorry for my interruption.
So why do we care about dark matter? Well, we care about dark matter because there is a great amount of it, both now and in the past history of the universe. These pie charts represent the energy budget of the observable universe. So in the current era, only less than 4% of the energy budget of the universe is made out of atoms that you and I are made out of, or known particles, known physics. The remainder of the 95% is unknown physics to us. And of that, about 25% is in dark matter. I'm going to talk about that part. There is about another 72% that is in dark energy that I'm not going to talk today. At the same time, when the universe was about a little less than 400,000 years old, the energy budget of the universe then was only about 37% in known particles, atoms and nucleons, photons and neutrinos, and dark matter represented then the remainder of about 63% of the energy budget. Also, we care about it because we find evidence of it in many different astrophysical observations and systems. However, we do not know what it is. We do not know its nature. Now, I'm going to briefly go through a few of those examples where, through astronomical observations, we have found evidence for dark matter. I'm going to refer to dark matter sometimes as simply as abbreviated as DM. So one line of evidence comes from galactic rotation curves. You all know that the galaxies have stars, and those stars rotate around the center of the galaxy. So for instance, our sun rotates around the center of our galaxy once every 250 million years. Now, why stars rotate around the center? They rotate due to, there is a need for a centripetal force. That centripetal force is provided by the gravitational pull of all stars and matter at a smaller radii compared to the radial distance of any given star to the center. Now, if all the matter that we can account for is in stars and in the interstellar gas, then based on that, on the profile of that matter, which we take from the visual, we can calculate the profile of that gravitational potential, and in turn of that rotational speed of stars from away from the center of the galaxy. So, for instance, this is the rotation velocity, the magnitude of rotation velocity in kilometers per second, and this is the radial distance from the center of a given galaxy. This is in thousands of light years. You know, as you know, a light year is the distance light travels in a calendar year. So we would expect that that speed would drop with distance if all the matter is in stars and interstellar gas. However, from observations, we see that that's not the case. We do see that we need more mass, more matter. In the case of our galaxy, the Milky Way, if you were to integrate all the way to about 100 kiloparsecs, so 1 parsec is a little more than 3 light years. So if you were to integrate all the way to 100 kiloparsecs, you would get to have that you would end up requiring 10 times more matter than the observable one. We find evidence for dark matter also in even larger systems. As you know, galaxies are the Milky Way, together with Andromeda, Triangulum, and some smaller galaxies represent the local group. The local group is part of a cluster. Galaxies exist within clusters of galaxies, and we can measure the velocities of those galaxies, and from that also derive that there is definitely more matter than the one that we can account for through visual observations. And it is significantly more. It's of the order of 5-6 times more dark matter than regular matter. We also find evidence for dark matter in even larger systems. Occasionally, galaxy clusters collide with each other. By collide, I mean they pass through each other. This is the known example of the bullet cluster. This is 2 clusters here that have already passed through each other. Now, galaxy clusters are made out of galaxies and dark matter and gas. Gas that is cluster gas, that is gas between the galaxies. When that interaction happens, what you expect is you don't expect galaxies to really cross each other because they occupy a very small amount of volume compared to the system. But what you expect from is that gas, because you have 2 gases that cross each other, they would decelerate. And that is what we see indeed through X-ray observations. And this is what we call in particle physics baryonic, which means regular gas, mostly protons. However, the gravitational potential, which we observe through gravitational lensing, seems to have progressed further out. It seems to have not decelerated as much. Gravitational lensing is the fact that light bends when it passes through a strong gravitational field, simply because space-time itself is deformed. We also find evidence from what we call the cosmic microwave background, which is coming from when the universe was about 400,000 years old, as I mentioned earlier. We find indication for dark matter from the observed distribution of galaxies. So this is from the Sloan Digital Sky Survey. This is every little dot here is a galaxy. We are at the very center. Redshift is a measure of distance. Whirlpool Galaxy M51 is at a redshift of 0.0015, so it's very, very close to here. So you see all those galaxies that we have detected, and you see that these galaxies are not distributed homogeneously. You see there is these filaments, these clear filaments. that filamentary structure is a prediction of dark matter. We also have suggestion for another line of evidence for dark matter from what we call in cosmology the growth of structure. Growth of structure says that stars were created first, then small galaxies came to be produced after them larger galaxies, then small clusters, and then large clusters. We also have evidence from individual strong lensing measurements of background objects, typically further away galaxies, and also from the success of what we call the Big Bang nucleosynthesis, which means just the prediction of how many elements were produced, hydrogen and helium, and a slight amount of lithium were produced at the very first seconds in the history of the universe. Now, so the significance of matter is that it's there and want to understand it, but we are also searching for new fundamental physics. We understand that this is not regular physics. This is not the known physics. So for that, we built many different classes of dark matter models, meaning many different classes or families of theories. I'm going to be talking about the case of the weakly interacting massive particle or massive particles, the WIMP or WIMPs, which in that case, dark matter is an actual particle which interacts through some physical properties physical processes which we don't know but we can model, to non-physics, meaning non-particles, particles that we have detected in experiments in labs. So the chi letter, the Greek letter chi, will stand for the dark matter, the letter for the dark matter particle. It turns out that if that's the case, these particles existed even at the very early stages of the universe, where the universe was extremely hot and highly energetic. And it was what we call, it was like a hot, very, very hot soup, or if you want appropriately, a plasma. And at that time, these dark matter particles would find each other easily and annihilate, giving non-physical, non-particles. But also those non-particles could also find each other, annihilate through some physical processes here, and give us back dark matter particles. So it was a two-way stream. That's why I draw the line of time in both ways. However, as the universe cools down, that energy drops, and inevitably, this line, going from the right to the left, becomes weaker and gradually phases out. And that results in the actual dark matter, number of those dark matter particles also decrease. Now, for certain choices, it turns out that we can have the proper amount of dark matter that we see today, meaning that about 23 to 27% of the total energy budget of today. If that's the case, we are talking about the dark matter particle that is about 100 giga-electron volts, or about 100 times the mass of the proton. It's a rough order. It's within a factor of 10 or so. So it's not exactly 100 giga-electron volts. Now, a giga-electron volt is a billion electron volts. An electron volt is the amount of energy an electron would gain through a 1-volt battery. So imagine you put a billion of them, a billion of those batteries in series, that electron would gain 1 GeV, a giga-electron volt, GeV in energy. So we're talking about particles that have mass that is 100 times that. And those particles, by the way, exist, and they pass, even as we speak, through our bodies. There is about 1 per liter. If that's the case, there is about 1 per liter in our location, and that 1 per liter particles are crossing through our bodies at the velocity of about 200 kilometers per second. So they're continuously crossing through us. And because they're continuously crossing through us, we can actually search for them. One way we search for them is we build underground, deeply underground experiments where we purify elements like xenon or argon or germanium or silicon and put them as targets so that maybe a dark matter particle would scatter with one of those target elements and give us a signal. What we also do is we try to produce them at the lab, at colliders, like the Large Hadron Collider in Geneva, Switzerland, where what you're doing is you're taking, in this case, protons, you are accelerating them, you're giving them extra energy, and at some point they collide, and you hope that they have enough of energy to produce these dark matter particles. If you've ever heard people saying at LHC they're trying to reproduce conditions of early universe, that's what they mean, that we are trying to get to high energies, such energies that existed in the early universe in the medium. And because the universe and our galaxy is so large, there is always the possibility that those dark matter particles may occasionally find each other, have some physical interactions, and annihilate into non-physical particles like quarks that make out the protons and the neutrons that we are made out of, or bosons, which are the carriers of forces in nature, or leptons like the electrons or muons or tau leptons. And after non-physical processes, those will end up giving highly energetic known particles like the proton and the antiparticle, antimatter antiproton, electron and its antimatter particle, the positron, or neutrinos, or a lot of photons. And it is the searching of those products that we are trying to achieve through a multitude of detectors and telescopes, both on Earth and in space. Now, why antimatter cosmic rays? Well, as you may know, every time an antimatter particle finds its own matter particle, it would annihilate, giving gamma rays. So there is very little antimatter out there because it cannot stay forever. At some point, it will find a positron will find an electron, and they will annihilate, giving gamma rays. The same with antiproton. So nature doesn't produce many antimatter, also in terms of continuous astrophysical processes. There is some process that can give us antimatter cosmic rays. As you know, cosmic rays are highly energetic particles, charged particles. That's what we call cosmic rays. So the sources of cosmic rays are supernovas, and more specifically supernova remnants, the environment, the disturbed environment around the supernova explosion of a very massive star. So those environments produce regular cosmic rays, regular matter cosmic rays like electrons and protons. Those particles then start propagating in the galaxy. This is a sample, I don't know which galaxy that actually is, but let's assume that this was the Milky Way. What happens is those particles diffuse. So they have this random 3D drunken path within the galaxy. And that has to do with the structure of the magnetic fields. So occasionally those protons, let's take a proton, occasionally that proton may find a proton of the interstellar medium gas, collide, and produce other particles. And that's the moment it may produce antimatter cosmic rays. And those we then may be able to detect at our location in the sun. However, this is a very rare process. And because it's a very rare process, the production, the expected fluxes of antimatter cosmic rays are highly suppressed. However, dark matter is an entirely different thing. Dark matter is neither matter nor antimatter. It doesn't care about matter or antimatter. It doesn't have a preference. So if dark matter was to be two dark matter particles were to find each other and annihilate, they would give democratically equal amounts of matter and antimatter. So you have this source that can produce significant fluxes of antimatter if such interactions of antimatter annihilations happen often, at a high rate in the galaxy. Also, we can make many, like everything else in astronomy, we can make connections to different observations. We can make connections between cosmic ray observations and gamma ray observations, or radio observations, or microwave observation, or X-ray observations. This is what we call sometimes multi-wavelength approach or multi-probe approach. What it means is we are studying the same physics and the same physical properties, but through a multitude of observations at different energies. Now let me say a little bit about the AMS. So this is the International Space Station, or an artist's drawing of the International Space Station. This is where AMS is located. AMS is a quite large detector. It's the size of a big refrigerator. It's about 3 meters tall and about 1 and a little more 1 by 1 in the other 2 meters in the other 2 directions. It's a complicated detector. It was launched and placed on the ISS on May of 2011, and it will collect data. We expect it will collect data for about 20 years or so. It will measure a lot of cosmic ray species, very different nuclei, many different nuclei, including it measuring positrons, antiprotons, and hopefully other antinuclei. Now let me say one of those first early results was the cosmic ray positron fraction. This is a measurement of antimatter to matter elements. So the positrons are the antimatter particles of electrons. So you take the positron flux over the positron plus electron flux. And this is a spectrum. So the ratio of those fluxes is what we call positron fraction. And here is over different energies. And energies, again, is in giga electron volts, or just GeV. What you see is it drops down initially. It starts at 0.1. So at low energies, there is, for every 10 electrons, there is maybe 1 positron. At about these energies, 5 to 10 GeV, for every 20 electrons, there is 1 positron. And at these highest energies, for every 5 electrons, there is 1 positron. So it's changing. That ratio is changing at different energies. Now, we also notice that it's quite smooth. It doesn't have significant features in itself. And the other thing we know from the observation is that all those electrons and those positrons do not come from a preferred direction. They come from any direction of that the detector can say. There is no preferred direction on the sky from where those electrons and positrons are arriving to the detector. Now, what is important here is the rise. It's the fact that this thing, not that it went down with energy, but then that it increased and went up. And at some point it flattens, but it's not very clear at this moment how exactly it does. So what is interesting is, it's interesting because the known sources of cosmic rays are, like I said, are supernova remnants. So this is Tycho supernova remnant. Tycho detected the actual supernova in 1572. This is an observation of the disturbed environment around that supernova, where in X-rays by the Chandra detector. So we understand that we have a measurement, and we understand that cosmic rays come with what we call a spectral parallel, meaning that if you were to write a flux versus energy, it would look like a line that drops with, as in energy increases, it drops as a parallel. And some parallel, but those parallels are actually pretty uniform and universal. And this we call primary cosmic rays. This is the energy spectrum of protons and electrons that comes out of these environments. Positrons are what we call secondaries. They are not produced around this environment. They are produced in the interstellar medium as the primary cosmic rays perform their drunken three-dimensional random walk. So what we expected before the observation, and this is an observation from an earlier experiment called Pamela in 2008, was that this would drop with energy. It actually went up. don't pay so much attention to these low energies. I will show you in a moment that that's not a problem at all. This has to do with the impact of the sun. But the important thing here is the rise. So the rise of that positron fraction, which is the flux of positrons over the flux of positrons plus electrons, suggests that there is some additional source of positrons. So the question there you ask is, okay, there is additional source of positrons. Does that mean new physics? And what new physics are we talking about? Is it fundamentally new physics, like dark matter? Did we discover some entirely new physical phenomenon? Or is it new physics of the sources, of the known sources of cosmic rays, like the supernovas environments, or pulsars, which are rapidly rotating neutron stars, the remnants of very massive dead stars, the stars that have exploded. So if it's dark matter, let's take the dark matter case, and going back to my original drawing, what you want is you want to know something about the mass of this particle. You want to know, is it 100? I told you it may be about 100 GeV, but is it 100 giga-electron volts? Is it 10? Is it 1,000? You want to know something about this blob, which tells you how easy it is for those particles to find each other. And you also want to know something about, okay, once they found each other and annihilate, to what products they annihilate to. What products, what are the end product of that? So it turns out that if you're, so again, this is the expectation without dark matter, the vanilla pre-detection measurement. This is the actual measurement of 2008. The data I will show you in a moment have become better, but this is a little instructive here. In order to have positrons and positrons that are 100 giga-electron volts, you need a dark matter particle that is a little more than that. It's actually need to be something like tera-electron volts. Remember, gigabyte, terabyte, right? So 1,000, one tera-electron volt is 1,000 giga-electron volts in terms of mass. Remember the mass energy equivalence, the E equals mc squared. In physics, whenever we talk about mass, we can talk about mass and use units of energy because of that conversion. Now, we also learn by the actual amplitude of how high, how far away those error bars are from the actual measurement, from the actual theoretical prediction without dark matter, we can learn something about how often those particles find each other. It turned out that that was quite enhanced. What we call the cross-section was quite enhanced compared to first-order expectations, and that was interesting. And we also, as I said, we need to learn something about the final products. The final products ended that it needed to be something like electrons and positrons or muons. Muons were detected by Hess, if I remember right. Well, Hess detected cosmic rays, but they were detected, they were understood through, measured through, we measure muons nowadays through interactions of cosmic rays with the atmosphere. Now, the better data, so before I was showing you actually the red data points. With AMS, we developed much better data points, much smaller error bars, so we can derive more refined, we can have more refined modeling of dark matter. And we can have a more accurate description of what what's the allowed mass range, which can be, again, several tera-electron volts, quite larger than we initially expected. And specific type of end products. These are end products. These are electrons and positrons. These are muons, and these are what are called pions. These are unstable particles, but they are known particles from many years now from labs and other observations. And it may, in order to actually explain the amplitude, the difference from going from this dotted line to these solid lines, you would need not only to have the properties that I explained about this dark matter particle, but you will need an additional new particle, that this additional new particle would be a carrier of a new force, a force that doesn't exist in your and my interactions in everyday life, but it's the force for dark matter. It's the force for the dark sector, a kind of a dark force, a new fifth force in nature. I will stop that story there and I'll take a different story now of another type of measurement from antimatter to matter ratio, which is the p-bar, meaning antiproton to proton ratio. Antiprotons are produced in the Milky Way, and they are produced when high-energy protons come and have very hard collisions, what we call in physics inelastic collisions, with an interstellar medium gas, with your molecular and atomic hydrogen gas. Occasionally, when they find them, they will produce several particles, which could include antiprotons. We have observed and measured that antiproton to proton ratio. This is, forget about the blue part, just take the green part. This again comes from the Alpha Magnetic Spectrometer, the AMS detector, came a little later than the positron. And what we found was that for every, the ratio of the two is 2 parts in 10,000. So for every 100,000 protons that we observe at a given energy, around these energies, there is only 20 antiprotons that we find at that same energy range. Actually, this is called rigidity. Rigidity is momentum of a charge over momentum of a particle over its charge. It's the natural units that experimentalists and sometimes theorists use whenever we are talking about particles that are bending within magnetic fields. But you can easily be converted to energy in GeV, and it's very similar in these values. So the question is, could you have a similar kind of thing? Dark matter, find, annihilate, produce, in the end, protons and antiprotons through some blob, where blob is a lot of physics. And that comes with a lot of uncertainties, right? With a lot of uncertainties, meaning what we call background uncertainties, meaning how well do we understand all those physics that go into trying to explain that observation without having to include dark matter, right? Without having to call it dark matter from all the other things that you know, how well can you explain that? So the question it boils down is, how well do you really understand when a proton comes and collides with the interstellar medium proton, so from molecular hydrogen gas, how many such protons are being produced? How well do you know that? And the thing with that is that we do rely on lab experiments that most of them were from the 70s. The other thing was, how well do you understand the propagation of cosmic rays through the galaxy? So when I went through this figure, how well do you understand this figure, right, this drawing? And also, since we live on Earth and our detectors are orbiting Earth, but are well within what we call the heliosphere, the volume that is affected by the solar wind and the embedded magnetic field of the solar wind. This solar wind has an effect on our cosmic ray measurements that we call solar modulation. This is a physical effect by itself. How well do we understand that? So I'm not going to go talk about that because this is a little too particle physicsy, and also I can answer questions to that. I'm going to go directly for the more astrophysics part, which is how well do we model, what do we use in terms of observations, and what type of models we use to understand the propagation of cosmic rays in the galaxy. What we do is we develop numerical codes, and we run numerical codes, we run models that include information about the possible distribution of sources in the galaxy. Where are those supernova remnants? It's not just Tycho supernova remnant. There is one where it's basically between 1 and 3 per century. So where are those? How those particles propagate in this drunken path, which is diffusion. The fact that actually as particles are propagating within space in this drunken path, they are also change their energy in a semi-random manner, which is called reacceleration. Then effects like convection. Remember heat convection from your radiator. There is equivalent, a similar thing with cosmic rays convecting away from the galactic disk and at higher latitudes. However, for all this complexity comes a great wealth of data, of observational data. Among the most instrumental in that is Voyager 1. It's not the only, but it's among the most valuable ones is Voyager 1. Voyager 1 was launched in 1977 and exited the heliosphere and entered the interstellar medium around 2012. So since then, it has been measuring a more pristine spectrum of cosmic rays that is not affected by the presence of the sun. And as far as solar modulation is concerned, one of you mentioned about sunspots. Well, we've been measuring the sun for a great amount of time. And since we are measuring the sun, we've been measuring the sun for a great amount of time, we can model it on a very, literally on a day by day and on a week by week or a Bartle's rotation cycle by Bartle's rotation cycle. Bartle's rotation cycle is 27.5 days. It's the apparent rotation of the sun. We can also, and because of those many observations, we can also include the many different complexities associated with the fact that cosmic rays, as they travel through that volume that we call the heliosphere, are traveling and following very peculiar paths. They follow paths that depend on their charts, they follow paths that depend on their energy, they follow paths that depend on the time they enter the sun. But observations also are, we have observations both of the sun and now of cosmic rays with energy and with time and with charts. So while there is theoretical complexity, there is data complexity that can match it and can allow us to track that. So this is an example of explaining the time evolution of the observed cosmic ray spectrum with energy, and this is from 2011 to 2012. And this is different species of cosmic rays, different nuclei of cosmic rays. This is carbon, and this is boron to carbon cosmic ray spectrum with over energy. So flux over energy or ratio fluxes over energy. This is the data points, and the lines are the theory. So combining all these things together, we can end up and say, okay, this is the cosmic ray antiproton to proton ratio. These are the data points, and this is the theory. And there are bands. The bands represent the theoretical underlying uncertainty, the remainder of the uncertainty, after including everything else. So at low energies, we have solar modulation. At high energies, we have the uncertainties that associate with how cosmic rays propagate within the galaxy. In a big fraction of energies, we have this uncertainty that has to do with how easily you produce antiprotons from these collisions in the interstellar medium, and they are still large exactly because we are still relying a lot of data from the 70s. But having done all that, we can still find excesses. So excesses is like things like that. Here there is clearly some extra antiprotons, and even here there is some extra antiprotons. The error bars are quite small, and it's a little more difficult to see it. So how do we fit excesses in terms of dark matter? Well, again, in this drawing, I need to understand something about the mass of the particle. I need to understand something about the new physics going there, and I need to understand something about the end products, the known physics, how it connects to the known physics. Here I'm assuming that it connects to the known physics with the final products being some quarks. Quarks are the subparticles that make up a lot of the particles that we know. It's not proton and neutron for these quarks. This is called B and bottom and BB bar and B bar, bottom bar quarks. They are known particles. We have seen them for many years now, many decades in experiments, and we know them. This is the mass of the dark matter particle. Here we are assuming that the dark matter particle may be anywhere between 5 giga-electron volt to 3,000 giga-electron volt. And this is the cross-section in some units, which are not important. The important thing here is the dust line. The dust white line is called thermal. This is the theoretical prediction for those WIMP particles. The theoretical prediction on how much the cross-section, meaning that blob, should be to explain today's relic abundance of dark matter. Today, the fact that today dark matter represents between 23 to 26% of the total energy budget of the universe. And this blue lot and other blue blob are regions where there is an excess. There is a statistical preference for having a dark matter component. We think that this has nothing to do with dark matter. This has to do with these supernova environments, remnant environments. But we do think that this blob has to do with dark matter. And the reason for that is because we have seen in an entirely different probe, in gamma rays, and looking towards the very center of the galaxy, another excess of gamma rays, which, if it was from dark matter, it would require the same type of properties, the same type of mass, cross-section, and particle. So the same diagram here. Now, how many antiprotons would be coming from this dark matter particle? It's only about 5% of antiprotons, of the observed antiprotons, would be originating from those dark matter annihilations in the Milky Way. So I told you that for every 100,000 protons, there are 20 antiprotons. Of those 20, only one is originating from dark matter. So we are talking about a 1 in 100,000. It is indeed, in many ways, a needle in the haystack. We are also using other type of observations. We are observing other nearby dwarf galaxies like Draco, like Ursa Major, or Sextans. And we have tried to find from them, by observing them in gamma rays, we have tried to see if there is something that would indicate for dark matter. We haven't found anything. So we draw limits on that. And we can say that if dark matter was, say, 60 giga-electron volts and had a cross-section of 5 in these units, or it would be excluded. In fact, anything that is on the higher end is excluded. The larger the value on the y-axis, the more dark matter annihilations take place. So you can exclude that. How about other probes, other observations? Well, how about heavier, more massive nuclei? AMS has actually detected some anti-helium cosmic ray events. By detected, I mean it's not a published result. It's been a long time, since 2018, it has been, they've been talking about it, but they haven't published data. So how do you produce anti-helium or anti-deuteron? I'll show you, so you know deuteron, the isotope of hydrogen. Proton is the main, the regular H1 is the hydrogen, the regular proton nucleus. Deuteron is a nucleus out of a proton and a neutron. Anti-deuteron is a nucleus out of an antiproton and an antineutron. This is an antiproton, this is an antineutron. How would you produce such a particle, such a nucleus? You would produce it conventionally without the dark matter story by having a cosmic ray proton colliding again with your molecular and atomic hydrogen, but at even higher energy, producing now more particles, including more antiparticles, which then merge, or what we call in physics, in particle physics, coalesce into producing an antideutron. So the question there is, well, first of all, once the minute people talked about anti-deuterium or anti-helium, this is super exciting for us. And the reason for that is we have an estimate on how often these type of interactions happen in the galaxy. And we knew beforehand that this was extremely, the minute I heard about it, I went to my collaborators and said to them, we need to write a paper about that. That's very unexpected. And we all knew it was very unexpected. The sensitivity of the instruments was nowhere close to the expected conventional fluxes from interactions of cosmic rays with the interstellar medium. So what do you do with that? Again, you need to model all the uncertainties. Here I saw you for anti-deuterium. It's the same basic stories. You need to include solar modulation. You need to include interstellar medium physics. You need to include particle physics uncertainties, which involve with how often this thing, every time this collision happens, how many of those are produced and when they are produced, under what conditions they actually coalesce into an anti-deuterium. For them to coalesce, they need to come to be very on orbits that are very close to each other. So there are large uncertainties. In fact, this green band and line is a line about the antiprotons, the cosmic ray antiprotons that I was talking before. Look at the band. This is for anti-deuterons, and these are conventional antiprotons, conventional anti-deuterons, nothing to do with dark matter. For every one this depends on energy, but let's stick on this main central energy range of a few giga-electron volts. Or actually, this is giga-electron volts per nucleon for the more heavy, more massive nuclei. For every one antiproton, you expect, actually for every 100,000 antiprotons, you expect only one antideuteron. For every 100,000 antideuterons, you expect only one antihelium-3. For every 100,000 antihelium-3, you expect one antihelium-4. Every time you go from a nucleus to nucleus, you are losing a factor of 100,000. 100,000 to 10,000. The uncertainties are very large. The bands represent the uncertainty on that flux, which is orders of magnitude. But even if it's orders of magnitude, it's orders of magnitude within tiny, tiny fluxes. So it's still tiny. Dark matter can actually be, on one hand, a small component of the antiprotons, but the dominant component of all the other ones. And for that reason, we can actually estimate that while this detector, the AMS on board the International Space Station, would need a full 20 years to detect, a full 20 years plus to detect one antideuteron. This is at 6 years, actually, of observation. So this refers more to what the AMS would say in 2018. It would have already detected several antideuterons from dark matter. And while that same experiment would need thousands of years to detect antihelium events, it may have already detected antihelium events coming from dark matter. There is a different way of saying it. Again, this is, look at the dust line. The dust line is the prediction from dark matter as explaining that dark matter represents 23 to 26% of the energy budget of the universe. This is the theoretical line you want to be at. This is the antiproton axis. They are looking from antiprotons. This comes from looking at gamma rays. And the yellow line comes from detecting anti-helium. The fact that, and those are the excluded regions. So this is an excluded region, this is an excluded region, these gray regions are excluded, but this part is included, is okay, and those excesses are possible excesses. So it may be that a dark matter particle that has a mass of about 50 or 60 giga-electron volts and has the proper cross-section to explain the total abundance can explain all observations at once. And those are my, and I just finished. I can talk to my conclusions. My conclusions is that we use many different observations to probe. I will actually leave it here. This is more interesting conclusions. We use many different observations to search for dark matter, and through cosmic rays, we can add additional probes to observations that come from the electromagnetic spectrum. And that's it. Thank you.
Thank you, Dr. Cholis. Do we have some questions? Jim, you're muted. Jim, I can see you talking, but we cannot hear you.
I wonder if we could put the conclusions back up again?
Yes. So the conclusions were that we take, we search for additional components. Well, we found additional energy components with the proper amplitude for the dark matter particle. And we take all uncertainties, basic uncertainties into account. And that by observing anti-helium and anti-neutron events, we may have added other new probes to search for dark matter, which seem to be in agreement with gamma rays and antiproton measurements.
Other questions? I have one.
Yeah.
You mentioned black hole. I think you mentioned black holes as a possible candidate for dark matter, correct?
I mean, black holes could be a possible candidate for dark matter. That is true.
These would be extremely small black holes. Can you put limits on their mass?
We are trying to put, we are putting limits on the masses of black holes as a candidate for dark matter through different observations. So we set, for instance, towards the Large Magellanic Cloud and towards the galactic center. And we are trying to observe what is called microlensing, which is we are trying to observe in individual stars some slight aberration taking place between between observations taken significant times apart, years apart. So that would be dark matter, would be black holes with a mass similar to the mass of the sun. But we search for dark matter as coming from black holes in other masses as well. We search for dark matter as being in black holes that are many tenths of the mass of the sun through the LIGO interferometers in Washington through gravitational waves. Like the LIGO interferometers in Washington State and Louisiana.
Okay, thank you. Are there other questions?
Yes.
Yeah. Oh, go ahead. I was just going to ask, you're proposing that antimatter is being generated by collision of dark matter particles with each other?
Yes.
Is that what you're proposing?
Yes.
So when we started out, the one of the justifications for the existence of dark matter, it was that what is it called, the dumbbell cluster of galaxies? Wasn't that one of your first slides there?
Yes, the bullet cluster was one of them.
Yeah, the bullet, right, the bullet cluster. So didn't that kind of illustrate that dark matter doesn't affect itself?
Yes, that's good. A very good question. Yes, so it doesn't, but occasionally it does, right?
Okay, so So the proposal is that on the rare occasion when one dark matter particle collides with another dark matter particle, it can interact.
Right.
And so that's what your whole premise is. But what about dark matter particles colliding with regular matter?
So dark matter particles.
Wouldn't that also generate? Wouldn't that be also more likely to generate antimatter?
So when dark matter particles collide, so there are both. So this diagram, you can read it both from left to right and from top to bottom or bottom to top. So this is dark matter, this is dark matter. This is when two dark matter particles collide. The vectors here, the arrows have to do with the way you can read it. So when two dark matter particles collide and annihilate, they give you the regular matter. And yes, you can have collisions of dark matter with regular matter. Those collisions would not lead to annihilation. Those collisions would just lead to some slight exchange of energy, of kinetic energy.
Yeah. Well, it's kind of, it seems, I know the whole thing is speculative, but seems like the idea of, you know, well, I guess you're making some assumption about the energy of dark matter particles, and I don't know.
Yes.
It's interesting. It's interesting.
So we know that dark matter annihilates. I mean, we know that dark matter exists, and we know how much of it exists, right? So a model that is like this model predicts that if it annihilates, if they collide that they have a cross section, they have a probability of colliding. There is a distance that once they come closer than that distance, they will annihilate, right? And that is taken into account on how much dark matter is today. The fact that there is some dark matter today means that this has to have existed at some point. It cannot be zero and it cannot be infinity. It's some well-defined number for a given choice of dark matter particle mass, right? So you can constrain that also from how much matter you see today.
Okay.
And from that, you can say, yes, there will be collisions of dark matter with regular matter, and it will affect, they are also going to be very rare, but the result of those collisions is going to be a very mundane result. It's only going to be some exchange of energy. It's like, it's going to be like a ping pong ball colliding with, by the way, if it's 1 to 100, it's like a tennis ball colliding with a bowling ball, right? So the tennis ball being the regular matter particles. So the tennis ball just deflects the bowling ball, deflects by hitting the bowling ball, but nothing else happens.
Would an example of that be the kinetic energy that we see with stars orbiting? I don't want to say orbits, that's probably the wrong word, but the speed of the stars going around galaxies, where we would expect those speeds to be slower, yet they're not. Is that an example of dark matter interacting with regular matter?
This is an example of dark matter interacting with regular matter purely from gravity, not through any other collision. It's not that it's coming that close. It's just adding more gravity, more gravitational potential.
Okay.
Question?
Yes. My question is, okay, you have two areas of physics, relativity and quantum mechanics. And currently there's no resolution on combining them together. But the understanding is that someday there is going to be an approach, either string theory or quantum gravity. Does anything you're working on relate to that?
Not directly. I mean, if we figure out dark matter, right, we will definitely find new physics. Will that new physics be will that new physics inform us about string theory? Not directly, Will it inform us about quantum gravity? Not directly either. But if, for instance, we find nothing from the particle side and we end up saying dark matter is not a particle and it is black holes, for instance, in that situation, you are informing us quite somewhat. You may be able to inform about quantum gravity. You may be able to make a prediction to quantum gravity. String theory and quantum gravity tend to what happens is that they tend to you can derive models like what I said, theoretical models. You can derive theoretical models and new classes of models from there.
My understanding is that the Large Hadron Collider didn't find supersymmetry.
Yeah.
That was something string theorists were looking for, but so far have not found. So does that mean that quantum gravity is the leading candidate so far? We really don't know that much.
We really don't know that much. What happens with supersymmetry is that supersymmetry is a very large theoretical. It has very different versions of it. There is the slim version of supersymmetry, and there is the thick version of supersymmetry. Meaning slim, meaning very minimum excess stuff from what we call the standard model, which is the known physics, or more extended version of supersymmetry. The LHC, what it does is it hasn't found, indeed, it hasn't found signs of supersymmetry. That doesn't mean that there is no supersymmetry.
Right.
But what it does mean is it's lost a little bit of its mathematical beauty, if you want. It becomes more coincident, a little more coincidental that maybe you can always say we didn't build LHC with large enough energy. That if we had made it to be 10 times more energetic, then we would have found it, right? So we need to build a 10 times more energetic collider. And then we can exclude supersymmetry. Yes, that's always a possibility. But in theory,
I have a question for you. When you're talking about the makeup of the universe, and when you constantly hear about the fact that dark matter takes up probably 35% of the universe, why do we have such a hard time discovering it?
Yes, well, that's.
I mean, it's a
it's the end of my life. I don't know. I mean, why we have a hard? Well, it's. We knew it was not going to be easy because we had been detecting dark matter. So the galactic rotation curves are actually the velocity distribution of galaxies, which was the first chronologically the first detection, if you want, of dark matter. The first measurement that gave us hint for dark matter came from the 30s, right? So we are 90 years later. And in the last 90 years, we have increasingly been finding more signals for dark matter through the conventional standard astronomy, and yet through the more particle physics, high energy physics, we haven't. Or, I mean, part of the reason is we didn't have the instruments, though, okay? We didn't have the instruments. Before 20,000, we didn't have the proper instrument to search for it. We knew that. We knew that if we were to detect dark matter, all these instruments that I was talking about here were to take place. All these instruments came around, started becoming sensitive enough for dark matter around 2010. So they've been placing constraints of dark matter in the last 10 years. This came around 2009, 2008, 2009. These also came around the last decade or so. So we have had a hard time, but we haven't had a hard time for the last 90 years. We have had a hard time for the last 10, 15 years. So one can say you can be patient, right?
So we're still saying we're in a very, very big state of infancy in the discovery of this, is what you're saying, still to this day.
Well,
what I mean, infancy, we're still just starting, right?
we were hoping we were gonna. Well, I mean, when I started this thing, I was hoping that by 2021 we would have found it somewhere, and we would be constraining the properties, right? Which is to some extent what exactly I'm trying to do here, right? Because I am saying that if you trust those observations, you have constrained those properties here, and they are this, right? It's only dark matter is this particles. But the problem with that is, believe it or not, actually astronomers and astronomical observations, people don't trust them so much as they trust lab experiments. So people are more skeptical about anything that comes from the astronomy side than the astrophysics side that they are from a much more broad experiment setup.
Would you agree that the would you agree that the uncertainty about dark energy, which is a more recently understood or recently discovered phenomena, and which dwarfs dark matter even, causes major uncertainties in the assumptions used in looking at dark matter?
So dark matter and dark energy, they differ in one very important manner. Dark matter causes gravitational pull, right? So that's very, in that way, it is much more mundane than dark energy. Dark energy, in many ways, is even more exotic in its nature. What uncertainties over dark energy cause uncertainties over dark matter, mostly on how much of dark matter there is. So it's true that different observations, we have observation of supernova remnants, right, of supernova explosions, and we use them as standard candles or standardizable candles, and to measure distances. And from that, we can get an idea about the Hubble expansion rate. We use the CMB and the measurement of the CMB to get and through the Hubble expansion rate, we learn something about dark matter and dark energy. We use the CMB to learn something about dark matter and dark energy. Those type of observations don't agree so well. And that means that's why I said it's between 23 and 26%. So this is, so I tried to not divert too much on that, because so I showed you two different pie charts which are intentionally a little inconsistent. One says 23%, right? The other one, if you pay attention to it, says 26.8%. That is two different measurements in some sense, and there is some uncertainty on exactly how big it is. It's whether it's 23, it's 24, 25, 26%, that depends. So that has an effect on the dark matter modeling as well, right? Not knowing exactly how much it is, but it is that much. It's not going to be 20 and it's not going to be 30 anymore. We are confident that it's between 23 and 26% or so. So yes, and dark energy is the one that dominates how much that is. That the conventional matter is the 4.6 to 4.9% that we know. This, the size of this pie chart affects the size of this pie chart to some extent. And yes, it trickles some uncertainty, but it doesn't trickle uncertainty in terms of its nature. It trickles uncertainty only in terms of its abundance. Is it clear what I mean by abundance? By how much of it there is, right?
Thank you for a great presentation.
Thank you for having me here.
Yeah, I hate to do it, but I think we have to let our guest speaker escape from us as the hour grows late. If I can sneak in one last question.
Yes.
If you think of a spiral galaxy and its stability as it rotates, in terms of the spiral arms being reasonably stable, what distribution of dark matter do you need to maintain that stability? And if it's at all odd, what would cause it to have that distribution?
So dark matter has this. So what I didn't show is the actual expected distribution about dark matter. So the thing with dark matter is it actually expands much further out. So while so if dark matter was to interact a lot with regular matter, it would damage spiral arms, it would damage filaments, it would damage all these beautiful small structures that we find. It would make it more diffuse, it would make it more thick and less refined, if you want. At the center, but at the same time, most of the dark matter, in terms of where it exists on the outskirts of the galaxies, meaning further away from where the galactic gases and the stars are. So, and for that, to some extent, that prevents galaxies from accelerating even faster, if you want. So in the figure I had here, right, this is in thousands of light years, right? So take, for example, our galaxy, right? Our galaxy spiral arms are what? About 3, 5, 7. I mean, we are in one of the spiral arms, and but so we are 8.5, but it's between about 10 kiloparsecs, right? In the inner, most of this structure that we call the spiral arms are in distances that are less than 10 kiloparsecs. Well, actually, this is 30 kiloparsecs. Sorry, this is actually 3 kiloparsecs, right? So in these distances where you see the spiral arms, you see the deviation between the expected, what I call the expected, and what is observed is actually small, right? So dark matter is a small addition here. Where it becomes really big is further away. So the reason we can do that, we can really say that, initially people said, when most of the data initially were here, right? And initially people said, you're not measuring something right? It took observations of many different galaxies, and at the same time at large distances from the center, to really see the strong deviation and be convinced about the strong deviation. And most of it actually comes, most statistically at least, most of it comes, in this specific example also, from the 21 centimeter hydrogen lines, right? So this is what? This is molecular lines, right? I'm assuming it must be 21, must be molecular lines. So molecular hydrogen. So this is very far in the very outskirts, far away from the spiral arms. Dark matter wouldn't mess up the spiral arms. It cannot mess up. There is not enough of it, and even if it was more of it, it doesn't interact that much with the spiral arms.
Again, thank you, Professor.
Thank you. Have a good evening. And thank you for inviting me.
Thanks.
All right, everybody. It's going to be 40 degrees this weekend, and it might even be clear. So it'll be like summertime again.
Ooh.
You bet.
Yeah. Right. We'll see.
We'll see.
I'll believe it when I see it.
Right with you, Doug.
I mean, this last Tuesday was probably the first night I've given up that it was clear in months. Only because
Really?
it was way too cold.
Yeah. Very, very good. It was nice doing this tonight. What time did he start actually? Because I got in a little bit late. What, about 8:30?
About 8:30.
Oh, good. So I missed about 5 minutes. That's all. Okay, good.
Well, thanks to Doug, it's on YouTube if you want to catch the repeat.
I'll
We had
absolutely do.
35 below zero wind chill this week in Minnesota.
Well, you know.
So, you guys.
So Mark,
Hey,
Mark Ketzinger, for the record, we had 16 on YouTube, and I think we had like 32 max. Did anyone see what the maximum in the Webex was?
I did not see. I didn't.
I mean, I would probably say 48, 46 to 48.
Isn't there a?
I saw 31 max on Webex.
Okay.
Look, we don't have hurricanes. We don't have forest fires. We don't have tornadoes to speak of. No earthquakes. You know, all we got is 11.
Yeah. So we had a max of 16 on the YouTube video. So total attendance was 47 then.
That's great.
Super. That was maximum of 16 concurrent. There might have been more.
Yeah, that's true. People could have come and gone at different points. That's true.
Because there were 36 playbacks.
Really?
36.
This is the first time I got in on the WebEx, but a lot of times I view the YouTube after. So I just thought tonight I thought I would join in, but you can count me as a lurker.
Well, thanks for joining us, Russell. It's great to see you.
It was 34 playbacks is what's listed here.
Okay. Hey. Good night, all. Great seeing you all.
All right.
Have a good night.
So for those on WebEx, I'm going to stop the stream. I'm sorry, on the YouTube. I'm stopping the stream now.
I think we're all about to hit a wall of the wall of sleep.
Okay, I'm ending the meeting.
Bye.
Night, everyone.